Y to delta. Yeah, Y to delta systems. And when we look at what we had with the Y to Y system for three-phase, basically power generation to delivery of a three-phase load, we can also go back and start talking about how do we analyze a system when we have what we call a delta connected load. Now, with a delta connected load, instead of having a neutral point like we saw with the Y source with the delta connected load, we're connected literally in a delta formation, in which for here we actually have A to B, and we actually denote that as capital A to B, and then capital B to C, capital C to A. And so how do we actually work and solve and analyze a system when we're considering voltages or currents with a Y to delta balanced three-phase system? Well, just as before, remember with the Y to Y system, all we had to do was basically say, okay, we have a Y to Y system, they both have a neutral point, the sources are all separated by 120 degrees. The load is, each phase has the same exact impedance. Well, with this idea of a balanced system, we can also convert essentially a delta load into essentially a Y load. And when we do that, we can actually appropriately solve the system by per phase analysis. Now, how does that conversion actually happen? And how do we actually consider a delta connected load in which the phase currents here are actually moving from phase A to B, and then from B to C, and then C to A? Well, what we need to do is actually first consider what the line current actually is. And in order to do that per phase analysis, we have to go back and consider the fact that there's a relationship between a delta connected impedance and then a Y connected impedance. And that relationship is very, very, very simplistic. A Y connected impedance is actually nothing more than Z delta divided by 3. And by that conversion, we can easily convert a Y to delta three-phase system into a basically Y to Y system. And once we do that conversion, that means that we have converted into basically a system where the source and the load both have neutral points. And when we have neutral point conversion, we can actually do per phase analysis. But how we actually relate the current, the phase current, that's actually in a delta load versus what's actually in a Y load takes a little bit of extra consideration compared to what we saw in the prior video when we looked at basically that phase current from basically a Y to Y system. Okay, Y source to a Y connected load. So the first thing that we do is for basically those line currents, IA, IB, and IC, all we do is convert basically to a single phase equivalent and solve. And once we've actually converted basically the Y to delta system into its Y to Y, and we solve single phase for that line current, all we have to do is basically say, well, we have basically a value for IA and IB and IC, but we take IA and we just divide it by the square root of 3 at an angle of negative 30 degrees. And once we've done that, we actually have appropriately found the phase current IA to B, which totally makes sense that there's going to be a conversion basically for that line current right there, because now we're going from basically the source to the load, but instead of going from basically A to N, now we're going A to B. We're actually going from phase A all the way down to phase B in basically that load itself. So there's going to be a conversion factor that involves dividing by the square root of 3 at an angle of negative 30 degrees. And the same thing can actually be said about the voltage. The voltages are offset, the line-to-line voltages, and how we actually look at that we're going to get to in the next video. But let's keep with the introduction of a Y to delta system and looking at the currents themselves. Now, the nice thing is with a balanced system, guys, is once we found IAB, finding IBC and ICA, piece of cake. All we do is take IAB and separate it for each phase by 120 degrees. That's all it is. Basically just a balanced system, balanced three-phase system, is once we find that specific current, whether we're talking about phase current or line current, then whichever one we're talking about, all phase currents are separated by 120 degrees, all line currents are separated by 120 degrees. So in this case, with a Y to delta system, all we have to do is convert to a Y to Y, solve single phase. Once we actually get that single phase current, all we have to do is just convert that right back to an IAB by dividing it by the square root of 3 at an angle of negative 30 degrees. Guys, it's Miller time after that. So here we go. Only thing that's the difference between the prior video example and this one is that I actually tacked on a Y to delta, a balanced delta and delta load here, in which we actually have 90 plus J30 in each phase. So what I did was basically say, okay, well, ZY is equal to Z delta divided by 3. Boom. 90 plus J30 divided by 3 comes out to be very nicely 30 plus J10 ohms. Did it actually mean for that to happen? Yes, of course, because we want to keep it simplistic, right? So therefore, now we actually have an appropriate Y to Y system, Y source, Y load. But finding IA in that single phase equivalent is very simplistic by KVL. All we do is take 120 volts at an angle of 0 degrees, divide that by the equivalence, 10 plus J3, and the equivalence of 30 plus J10. Very simplistic. But that gives us a line current basically of 0.951 and an angle of negative 18 degrees amps. How do we consider that for the phase current that's actually in the load that's going from A to B? Because remember, this is capital A to N. In fact, actually I should have written this up here right here. That is capital A to capital N. And the current that's in the line for the conversion is actually the same in the converted load, A to N. But what's A to B? What is A to B? What is that current that's actually in that phase going from A to B, or B to C, or C to A? How do we actually consider that? And sure enough, all we have to do is take IA, divide by the square root of 3, at an angle of negative 30 degrees, and bam, we get 0.549 at an angle of 12 degrees. And guys, to find IBC or ICA, going from B to C or C to A, all you have to do is take that phase current of IAB, separate it by 120 degrees. IBC is separated by negative 120 degrees, and ICA is separated by positive 120 degrees. We tack that on. And guys, that's how we actually deal with a basically three-phase Y to delta. We convert it to a Y to Y, and then we solve appropriately. Next video we're going to look at is actually dealing with voltages. How do we determine basically line voltages? How do we see phase voltages? How do we deal with a Y to Y system? How do we deal with a Y to delta system? And after that, we're going to get essentially into the power aspect of that, which is going to basically take everything that we have talked about with single phase power and we're going to pull all of this together. It's going to be really interesting stuff. All right, see you guys then. I'm going to cook dinner.